All right, so you've had a lot of lessons on what FRP, the different materials, how it's made and all that stuff, and I probably have a little bit of that in here as well. But really what I'm here today is I was faced with having to learn it, right? I'm an experienced structural engineer. I know the design of regular reinforced concrete very well, but I know nothing about FRP, right? But what happened was, one day, working at ACI, a federal agency called and said, you know, we're hearing an awful lot about FRP and we would really like just to have some general guidance on learning how to design with FRP. We would like, is it ready for us to start speccing it in our jobs? Can we start getting this information into our system? And I said, okay, yeah, I think we can help you out with that. And I said, well, you know, I could hire a contractor or whatever that is knowledgeable in FRP, and they can sit there and say, nah, let's not do that. You know, I would like to have some information from a perspective, because this is what's going to happen with the federal agency. These people are going to know nothing about this. How do we get them from point A to point B so that they can start designing with FRP? So I said, okay, well, I'll give it a try, all right? So I sat down, I started looking at it, and I had to do all the learning. I haven't been going to these workshops like this. I certainly knew there was a 440 committee. They were working on a code. I knew there was lots of good information out there. So I said, okay, I'll kind of pull in 440 people as I need to as I'm going along here. But how do I start? And I think their first question to me was, all right, is it really ready for prime time? So, you know, interestingly enough, this all happened around the pandemic, so I couldn't go to the office. I was stuck with whatever I had on my computer. And the first thing they wanted was case studies. They wanted some assurance that this is ready, right? So I had to go along with the learning curve as well. And I found plenty of information out there that shows that this stuff has been in service for quite some time, you know, starting back, 1990s more or less. There are plenty of papers out there that show that have done some evaluation of these structures that have been in service, and everything is looking golden, right? So you assemble all this information, and that was great. They said, okay, we're sold, so let's go to the next phase. What do we need to do? I hear you got a code coming. I said, yeah, and of course we started to play that game where, when is the code going to be done, right? And it's like, well, it's a committee, so they're coming along, and I always had to kind of put them off a little bit. But they wanted to make sure that the code was done before they would adopt anything, so we're always kind of playing that game as we were starting to learn. But they were very happy to hear that there was a code. And then they said, okay, so then what's the next step? We hear there's a code coming. That makes us feel good. What are the limitations of this thing, right? So what is the next step in our thought process? Where can I use this? Where can I not use it? Of course, corrosion is the biggie, right? And that's kind of where you want to go for it. And they said, well, but what are the limitations, right? And then how do I think about it? We're all used to use steel, so they're thinking, boy, I'd like some comparisons between steel and FRP. And what is this material exactly? What are the things we need to know just to use this bar, right? So first of all, the limitations that kind of came out right away were fire. That was obvious, and everyone's going to say, okay, so can't use it for fire. But the group of people I was talking to were very much building people, right? So everything, their frame of mind was always, I'm going to build a building, right? Well, I mean, this material, and you've already heard it here, there's a lot of great applications that don't require you to go multi-story, okay? Or that you have to have a fire rating. So I think they were quickly over that. And then seismic was an issue. Once again, if you're thinking buildings, I'm going to build a 5-story building or whatever, and I can't build it in any seismic, well, what the heck? Why would I even bother? And of course, the more we talk and the other applications that they can provide, waterfront, structures and all that stuff. They're like, oh, okay, that's fine. I said, pre-stressed, for the 440 code that's coming on, pre-stressed is not covered. So I don't know if you all know that, how much of you guys have really got into that code yet, but it's only glass fiber. That's all that's in there. Carbon's not in there, basalt's not in there. So that was actually a good thing for this phase of where we're at. I'll get to that in a little bit, but I had to warn them that there wasn't any pre-stressed, and currently there wasn't any lightweight. And it's largely because we need more information, we need some more research, and we need some more ASTMs to make these things happen. And they were like, okay, fine, let's move along. And so then we started getting into the resources that are out there. 440 obviously is what I concentrated on. I did recognize that there were some AASHTO documents, FIB documents, Canadian documents. But, as I read the different documents that are out there, I found them to be all very similar. I was not finding massive amounts of different information from the different sources. So whatever one you're comfortable with, dive in, read those documents, and you're more or less going to get the same tune from the other institutes. So I had a lot of resources. I started to dive in, and the first thing I was thinking about was the design considerations. I'm a structural engineer. I'm not so much into the material, right? I want to know how to design it. I'm a structural engineer. So what do I have to deal with? So the first thing we came up with, okay, it's elastic until failure. Well, okay, I'm used to having steel. Steel has a yield plateau. I'm very much like, boy, what am I going to do without a yield plateau? And so once again, you just have to read, you get into it, and you start to see all these reduction factors. And boy, does 440, the code, really reduce the tensile stress. I mean, it is amazing all the factors. So they have this thing called environmental factor, and probably everyone out here already knows that. But for me, I was like, well, it's kind of a silly factor, but okay, it's like a big fudge factor. I guess, it's not. It's got 30 years or so of experience, but over time, as we get more and more experience with that CE factor will probably change, right? But it is a nice fudge factor for now, and it did make me feel a little bit better as a designer, going, how far am I going to get away from that elastic rupture, right? I mean, I need to get far enough away from there to make me feel comfortable. And so I started to see these lower phi factors that got that factor. And then you got the creep rupture that you can't go above 0.3 FFU. And I was like, well, damn, that's getting way down there. So I started to feel real comfortable really quick about using this, if they're going to penalize themselves so much, I felt like I could use this, right? And since I'm probably not going to be using it in a 10-story building, I'm going to be mostly using it for wharf designs or the things that you've been seeing, the bridge applications. I'm not really a bridge guy, so I'm not going to talk about bridges. I'm going to think about structures that, on the other side, right? In your world of structural engineering, you go down one of two courses. You either go down the bridge courses, or you go down the buildings. And so I'm on that side of the way of thinking. And then, so that made me feel better. And then also when I started to get into the designs and looking through the calculations, I was finding that for bending, deflection was controlling most of the time anyways. And so the stresses that I was working with in my bars were just so low that I felt, it didn't take me very long to feel very, very comfortable with designing with this material. So I'm just giving you one person's perspective who is learning and the things that they were seeing. The chart you see here is similar to the last presentation where you're seeing the different behavior of different types of materials. And so I don't know, for what it's worth, I didn't feel like it was that big of a deal at the end of the day. And then so you go to design bending, well, it kind of interesting, so how do I design for this? And I'm not going to get really into the nuts and bolts of how to design, because really this is, once again, this is my personal experience. And so what you do is you're trying to design it more or less for the balance point of either the GFRP rupture or the concrete crushing. So it's not the easiest calc in the world to do, but it's easily programmed. So as a matter of fact, you know, at the end of the day, we use computers to do everything these days. So you're going for this simultaneous rupture and crushing type of calc, but quite honestly, there's so many design examples that are out there for you to use. We're actually making a manual as well to help you come along into the understanding of how to design with this. So not from me, because I'm still the novice in this, so what you might hear me talking about is still things, I'm still fairly green, okay? But I'm really not having a problem with the design, okay? So that's kind of a nice thing. The column design is a little strange. Will here, who's in the audience, is one of our engineers, and he's a big designer and all these things. He always talks about the disappearing bars. And so since these bars are, we really don't count these bars in compression. In essence, they just become part of the concrete. They have the same characteristics as the concrete. And so in essence, when you're making your moment diagram, your bars disappear as you apply moment, right, or compression, which makes for a little bit of a strange interaction curve. But once again, the calculations aren't really all that different from, it's just slightly different types of material, slightly different behavior, but these are all equations that I'm pretty much used to. Shear, there's a little, you have to think about shear a little bit differently. Since you have lower axial stiffness in your bars, you tend to get larger cracks, okay, in shear. So we have to think a little bit, the limits on shear design is a little different. But once again, once you know those limits, the design is not really all that different than regular reinforced concrete. So really, the design, I just didn't think was such a big deal. But there were a few things that were kind of interesting on the design side that popped out at me and probably didn't hit me right away. And one of those things is, what does it mean to know that there's no plastic deformation? Well, it means there's no moment redistribution. So when you're thinking more like a building designer, I really like moment redistribution in my structure, just how I anticipate the cracks I'm going to receive. I mean, once you get to be a seasoned designer in reinforced concrete, you just know where the cracks are going to go. You know how the moment redistribution is going to happen. You put a couple extra bars here or there because you know you're going to get some restraint. I think I need to think a little bit harder about all that when I don't have moment redistribution. Okay, so you're going to have to want to rethink a little bit about how you might approach it from a steel standpoint for an FRP standpoint. Something else that kind of hit me was, okay, so we have this bar that was really strong in one direction, but hardly strong at all across it. So like for a dowel, the shear, we've talked about that, or you've heard that through. Well, that was a shock to me, and then instantly it's like, well, what about shear friction? What about those things? Well, the code is silent on shear friction at the moment. So it is, all of a sudden I have this thing that isn't good in that direction, and so what does that mean to me, right? Well, in brute force design, I'm not necessarily worried about that on a day-to-day basis, but there are situations where you're using your reinforcement as a dowel, and now you have a greatly reduced strength for those instances. So that's just something that now is in the back of my head. On the flip side of that, in talking to a lot of people, it's not a bad thing, especially that federal agency I was talking about. You know, they put a lot of stuff in the ground, like just, you know, slabs and stuff, and they have to put down slabs and pick up slabs all the time. And every time they have too much steel reinforcing, it becomes a huge headache to them. If they're to use FRP, you can demolish concrete much more easily because it just cuts those bars right in half when you scoop it up with like a backhoe or something like that. So, I mean, it can have its benefits too. Use it for its benefits. Other things that were interesting was, for bending, deflection seemed to control most of, the beam designs and slab designs. And then the questions I got from other people over time, it didn't really dawn on me, but, how do you splice it? And so it's just normal lap splicing. I think the code does say you can use mechanical connectors, but I believe as of now, there is no mechanical connectors that are available for purchase. So I guess those will be developed over time. But that's just something how you have to think of it. An interesting little paper that I ran across too, kind of give everyone an idea of, as I'm comparing FRP to steel, well, how much more or less GFRP bars am I going to be using in my design? And I'm going to give a rule of thumb, and everyone could admonish me later, but in essence, the more bending that you're designing for, in essence, you're going to have almost twice as much FRP as steel, as far as reinforcement ratios go. So this study was done for a bridge deck, and where they were comparing between girders, bent caps, so on and so forth. And basically, as you transition to a mostly compression-controlled element, it's 1-to-1 as far as reinforcement ratios go. And so, walls are going to be somewhere in between, all depending on how much flexure you're dealing with. But in essence, just as a what are we talking about kind of thing, I thought that was very interesting. And that was pretty much it for the design side to help me feel comfortable. The 440 code, if you've not read it yet or took a look at it yet, the commentary is very, very good. It does explain the different behaviors and why those behaviors exist in more detail, say, than maybe 318 does, mostly to bring folks like me along. So I really don't feel as though I need to kind of talk about all the different, integral properties. Those are things you can go and pick up on your own, and is not the focus of this presentation. But the shocker really was materials. So when I first started looking at this, I was just completely overwhelmed with all the materials stuff, completely. So if you're a manufacturer out there, you're going to need to calm down some of us structural engineers. Because as I started to go in, I started to read all the literature, and we're talking about all the different test methods you had to do, and all the different things, we're talking about UV rays or something. You're also saying, hey, these things have a difficult time in an alkaline environment. I'm like, what? I'm putting it in concrete. So I was kind of taken aback with all that. And yes, there was a lot of discussion about the different type of test methods and stuff like that, but at this same time, like I said, it was during the pandemic. I was not aware of ASTM D7957, and that calmed me down considerably, because otherwise I was looking at listing all of the test methods that you had to do, kind of like on the previous presentation you saw, where they listed all the test methods and all the limit values that were in there. I'll tell you what, I'll never get to know FRP that well. I'm just not going to do it. So when I saw that there was an ASTM for GFRP bars, and it set all those limits, and it set the bar sizes and the capacities, that was a huge relief. I was almost going to walk away from learning GFRP anymore at that point, because there's no way the federal agency was going to spend that much time and effort to accept that material. So if I am just saying from personal experience and talking to other engineers who aren't getting super close to this, you're going to need more ASTMs like D7957 that we can just spec on the job, because that's just the only way you're going to get it approved or get more people to use it. So that was one thing that really was hard to get over, but until I found that ASTM. And once again, had we all be able to sit together in the same room, someone could have just told me that right away, but it kind of freaked me out for a while. And as I was learning, so then, okay, all right, so I got this ASTM. I need to know a little bit more about this product. I think one thing that was interesting was when people talk about FRP, I was always thinking just the little fibers, like it'd be chopped fibers, and that they'd be thrown into a matrix, and that's how they made the bar. I was really surprised to see it was a continuous strand in there that they were protruding through. And I don't know, I just never thought that would be how they did it. And I thought that was particularly important when you start to think about fire. That if I was to lose my resin, that those rods are still there. So there's some capacity there that, for whatever reason, made me feel much more comfortable about this bar, especially when we start talking about things like fire and things like that. So I was happy to see that. The other thing that kind of threw me was the fiber volume discussion. So the ASTM does set a minimum fiber volume, but when you're going through the literature everywhere, boy, they kind of really just leave it up to you, the designer, to figure that out. And so I was glad to see that there was some sort of minimum in the ASTM, because that fiber volume in the bar can affect weight. So I can see that there's can be a lot of competition from manufacturers out there that I would have to wade through to say, I can give you this bar that's this strong, right? But it only weighs, a third of steel, or, a quarter of steel, or a fifth of steel. And I'm like, well, how can all this be for the same size bar? And it all comes down to this fiber volume. So for me, that was really nice that there was some minimum peg. Now, it might be interesting that as things go forward, if I call out ASTM, that's what I'm going to do. I'm going to be calling out this ASTM. I could see manufacturers saying, well, but I can give you a stronger bar, and you can get better values for the same size bar. I can see maybe, some of that kind of stuff happening further down the road, but at least I got a starting point, and a decent starting point for design. So that made me feel very comfortable. And so the interesting material properties, as I was learning and I was starting to read all the FRP side of things, the bars don't yield. That's already been talked about a lot today. For that ASTM, you basically get 1/4 the stiffness of steel, 1/4 the weight of steel, according to the ASTM. It's weak, the stress is unidirectional. And then, of course, the bond strength, and that's the other thing that's kind of interesting. You've got all these different types of surfaces. You guys already saw the different rods that went around, but, the ASTM sets a bond that you need to hit, and however you hit it, that's fine, and so I'm okay with that, right? So material properties, and that's as far as I had to really go as far as getting comfortable. The weird thing for me was, when I looked at it, that ASTM, you had the different bar sizes, but I have a different minimum guaranteed ultimate tensile force for each size of bar. Well, that's a new one, right? So it's not like steel, where I have the same ultimate stress, no matter what the size of the bar is. I have different ultimate stresses for different size bars. And I assume that's because of the shape of the bar, right? It's a circular, and you don't have a uniform stress across the section. I think, as you heard earlier, as you're transferring the stress from the concrete to the bar, it has to go through the glue, and then it hits the rod, and it keeps going further into the center. So it also it's kind of interesting that you pick up almost right away that maybe a round bar isn't the best shape for reinforced concrete. Yes, it makes me feel comfortable. It's something I understand. I know what a number 4 bar, number 5 bar, 6, so on and so forth. But it is a little strange that we have this different ultimate stresses, in essence, for each size bar. So for those of you who've not dealt with this before, I find that interesting. And perhaps maybe someday we'll go to a different shape that is more effective. But that'll be until people feel better about it. So that could be my ignorance, but for us structural engineers, I'm not going to do extra testing. I'm going to say I want ASTM, blah, 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 and just like I designed for steel, and I'm walking away. You know, if the manufacturer says they meet that ASTM, I'm going to believe them, and I'm going to use that product. So if that's not what I should be doing, then there should be some more warnings out there to the general public who's going to be learning how to use, to design with this product. So in the construction specification, I feel like I'm almost going to be repeating some things here. All the, learning about how to work with this. Okay, it's lightweight, it's great. Contractors love it for that fact. But one thing people don't talk about a little bit is that's a really rough bar. I mean, you're sending these bars around, they're all nice and smooth and they feel good. The bars I've been touching, the ones you actually get, man, you need gloves and you need one hell of a good pair of pants because you're going to be carrying around like this and it just rips your pants apart as fast as can be. It's no big deal, you just have to be ready for it, that's all. Storage on site, there is nothing I read out there that said you had to really pamper these things. The experience that I was reading out there is, this thing can be exposed for up to like 2 months before, so it's not like you have to run out there and get a tarp over this thing as soon as you put it out there. Once again, by just reading the general information that's out there, they really make you worried. And so you really have to kind of scratch underneath the surface to kind of find these other little things. You really have to kind of talk to someone, it seems like, which is unfortunate, there's enough, the literature really ramps you up as far as you're concerned. But once you start to learn everything and when you talk to people, you really back off really quick. So I don't know, that's just a little side note to the people out there that perhaps we've been overly cautious about explaining this material in our literature. Once again, there's no field bending. You've heard that, once the resin's set, there it is. But you can field cut it, and so, that's just something as a designer, you just have to deal with and have in the back of your mind as you're detailing. But to me, didn't really feel like that was a big thing. Cover requirements are a little bit different than regular concrete. Once again, they aren't dramatically different. You just have to make sure you use the code values, but you're going to be good there. So, that's pretty much it as a designer. Not an exciting presentation. But people thought that this might be something that you guys want to hear, is just one person's experience as they go through this. But really, once I got past, just the hoops that you have to go through and the material specifications that I need to use, I was instantly falling into a nice zone there. The fire, a lot of people get really worried about the fire, but since those fibers are continuous in there, and if you can anchor them in a protected zone, you can get a really low fire rating, but you can get a rating. And actually, the more I work with this, the more I would feel very comfortable, like up to a 3-story structure for myself. I would have no problem using this material for such instances. And so I'd like to see that progress, and I know there is some research working on that. Other things I'd like to see is just coming up with a seismic methodology. We won't be able to use the ones for current concrete because they depend on a lot of ductility, a lot of yielding, but I'm sure we could come up with a methodology for seismic for this material. It's going to take someone who understands how to adjust those things. I mean, we've done it for other things where we just have really low R values, and I mean, that's kind of a brute force thing. It'd be nice to figure out other methodologies, but I don't know if it's something we have to run to. But just as a designer, I'd like to see some seismic application. One thing in learning about the design, it's not really realistic, I think, for FRP columns, just regular reinforced, not pre-stress. I'm being told that realistically you're not going to go above 4 stories anyways, just because of how, it's just going to be so flexible that your structure, once you get above a couple stories, it's just not going to be a realistic design that you're going to do with FRP bars. So maybe seismic isn't something that we need to run to and figure out. However, I think there are a lot of ways you could use FRP in seismic structures, maybe not as the main reinforcement, but maybe as stirrups and ties and things like that. That would be great. I mean, if we could use FRP ties in moment frames and shear walls, I mean, we could really cut down the weight of those things. And if you could manufacture them solid, that would actually save a lot of lap space too. So, I mean, there's a lot of things out there that can be done that I would like to see as a designer. And of course, I would like to see an ASTM for carbon and basalt, so that those could be brought into the code. I really like to see that. And then, of course, pre-stressing eventually in the code. And that's what I'm kind of focused on there. And so my ending impressions of all this is I found that the tools were there to learn. The case histories are not hard to find on the internet. You can find many, many examples to make yourself feel better about it. It really opened my eyes, and my blind spot is what I told you earlier. I grew up on the building side of life, and so I have not really paid attention to all the other types of structures that are out there. And of course, pier designs, wharves, things like that, even, swimming pools, right? Anything where corrosion is an issue and you're not necessarily dealing with multi-story buildings, there is an application for this. And I can guarantee it that you will feel pretty good about designing with this in a fairly short period of time. So that is my experience. So I don't know if you have any questions here for, all right, Dave.
There's a working group about to start on carbon.
David.
Okay, David Lang, University of Illinois. I thought you made some really great remarks and some provocative remarks, and I especially was struck by your reaction that, gee, I don't understand some of the conservatism. It seems like everybody's cutting down the capacity in the code, and you use the phrase, this field is hurting themselves, not even taking full advantage of this. I wonder, this is where I want to invite your remark.
Yeah.
It's a little bit a sign of the heritage of how reinforced concrete came up as a system, and how FRP comes up almost as a materials topic, subtopic. And so you see, we have essentially the same mechanics of reinforced concrete that was set up in 1905.
Yeah.
That hasn't changed exactly, like same kind of stress diagrams and so forth. But all the issues with the materials that come, say, out of all the research from the 60s and 70s on aerospace materials and resins and fibers and so forth, that sort of has to bubble up through our system. And the end result is that it intimidates the heck out of a traditional civil engineer who's now getting this impression that we have a super complicated material in FRP.
Yeah.
That, I think, is more of a sign of the heritage of these communities rather than reality. They're just physical materials. And anyway, that's the remark, and kind of invite a response to that idea about maybe we've become overly conservative because of that background.
I sure feel like it. Yeah, just reading through all this material and trying to get into it and learn it, and I think this is way too conservative of a design. My personal opinion now, I don't know, just my impression.
Well, that remark, probably inspires other people to chime in with more knowledge than I have, or maybe than Matt has. But I think that's an interesting idea. I wish we had a few other people in the room that have been behind 440 that could help defend what 440 is showing.
I mean, I can get it, you know, I mean, you always hear, why did we have to wait this long to be this excited about using FRP bars or any FRP material at all? I feel as though I would have felt good easily 10 years ago using this material with what I've learned.
Okay.
And maybe the conservatism in the numbers maybe was more warranted than, I mean, every 10 years that goes by, right? You feel better and better about this material. I mean, 10 years ago by of, you know, case studies in the field. And so maybe I'm sitting here saying, duh, but I would have felt comfortable with what I've learned 10 years ago.
Thank you.
Yes, sir.
My name is Michael. The question that I've got is related to the UV degradation / temperature. How does it compare? Because when we talk about UV degradation, we're talking about time spent to sunlight.
Right.
When we talk about temperature, you can have the exact same time spent to sunlight in Michigan
Yeah, right.
versus Texas.
Right.
I was wondering if in the literature that you've looked through as you go through this phase, you could share some of the findings that you've had as far as to the temperature effect versus UV degradation exposure.
So yeah, there was some concern about the temperature, and actually that's one I didn't read as much about. There was a lot of literature on UV exposure, okay, and many case studies and many examples of testing after exposure, okay. So I feel really comfortable about, you can find stuff about UV. The temperature, not so much. There are limits that are in the construction specs, and they're fairly low. I don't know if they're low enough that it would be a concern in Texas, okay? But I could see there are certain situations where that limit, I don't know if it was 122 degrees or something like that, Fahrenheit, as far as storage on site. I know it's lower than what the glass transition temperature and stuff that you're worried about, you know, for exposure to heat, like in fire and stuff, but for whatever reason, there's storage on site in the specs. The spec I saw from ACI was down around the 120 degrees range. I didn't quite understand why that was so low.
Okay, I'll make sure that they don't keep it in an uninsulated container. Thank you.
But I just didn't read much more about that, and I didn't see a lot of literature on that or why that number was there like that. All right. Oh, yeah.
Again, Al Erickson, AIT. Just so you know, to sort of come off of Rudy too, there's an ASTM now for basalt fiber itself.
Okay.
It was passed in the fall, and I believe they just balloted and passed the ASTM to include basalt in the FRP bars.
Great.
So now those two concerns are now being quickly taken care of.
And just from my standpoint, until I get a basalt ASTM, you know, for a bar,
Yep.
I'm just not going to be able to use it. So
You're going to have it. It's
okay,
coming, it's coming
that's
right
awesome. And
along.
I hear basalt's a great solution too. So
It is.
I would love to use it.
They're good.
You know.
And then the other thing about the temperature, think about it that a lot of the precasters, and there was making a lot of precast beams and piles and things. What happens when we cure the precast? It goes up to 140, 150, 160 degrees. There's no effect on the bar. It gets warm and it gets cold. Until you get to glass transition, that's it.
So I'm a little curious for those who work on 440 here or other specifications. I'm not quite sure why we have such a low storage temperature for the FRP bars. That's in our specs. So I'm just a little curious about that, that's all. Once again, someone who's new to the material doesn't quite understand why things are the way they are. Okay, sounds good.
All right. Thank you very much, Matt.